Let's see what do without the slides today. Just as a, so your second assignment is up, and so if you look at the last problem, it's very open-ended, and it's very much of a design problem that throws out a problem. It's something for you to do, and what I'm expecting you to do there is show using somewhat of a precise calculations by choosing the materials in the picture. How can you get inter-subband energies just to match with that particular wavelength? I mean, that's really what I'm asking there. There are obviously a lot of other details as to how you actually build a photodetector and whether those transitions are allowed and things like that. I'm not asking you to look into those aspects. Those aspects are something for later in this course. Right now, just design something which has the right energy separation. And when you do a design, if you're just on a threshold of it'll, you must have a little bit of robustness. If you're going to detect 12.5 micron and your design is such that it's too sensitive to the thickness or too sensitive to the compositions, then it's not a very good design. So it should be a little robust. So that's, just think about it that way. And please ask me if you have any doubts or questions about that. So as I mentioned, towards the end of the makeup class last time, what I'm going to do now is today I'll do an overview of electronic devices, because to go to the next step, we need to understand what motivates us to create these compound semiconductor heterostructures. So today that's what I'm going to cover. This is chapter 3 in your book. It's obviously there are full-blown books or book series on device physics, but how many of you have had semiconductor device course before? Devices, where you do PN junctions, diodes, and okay, so a reasonable amount, but good. So much of some part of it would be an overview, but what I want to stress on today is why compound semiconductors. I mean, what role do they play? That may or may not have been emphasized in some of the courses you might have taken. And this is also, we go into a little more depth in that video, or rather the YouTube lectures that I have suggested. So I'll also, particularly the last 2 lectures where we talk about PN diodes and junctions. And so, please follow up what we are covering in class with the chapter 3 from Rocket's book and some of the videos. So just okay. Okay, so what we'll do is get started on. So this is kind of a summary of device physics, but with a flavor of compound semiconductors and what do they bring to the table, or rather, why do we use compound semiconductors in devices? So for that, we need to kind of step back and look at what we have achieved till now. We've understood electron band structure for various semiconductors. We understand that typically conduction band states are from s orbitals, valence band states are from p-like orbitals, and there's a gap. And you can control in a semiconductor, if you look at the band structure, typically E versus K. These states are typically filled and those states are empty. And one of the things you have complete control over in a semiconductor when you grow it, or when you after you grow it, you can put in dopants, right? N-type donors or P-type acceptors, and you can control where is the Fermi level. So if your Fermi level is somewhere close to the middle of the band gap, then by doping you can move it that way or that way, right? I mean that part we understand. And how do we understand that? So we have already seen the number of electrons in the conduction band, which we label as small n, is equal to so you have a density of states of the conduction band, and then you have an occupation function, which is the Fermi-Dirac distribution. And so that's the number of electrons. Density of states, remember, is the number number of states between, or the density between E and E plus DE. So you need to kind of multiply by DE to get the number and this many are occupied, and you integrate over the whole state, right? So that's how you get your electron density, and you integrate it from, as we have discussed earlier, from the band edge to the top of the band, but generally the Fermi function dies fast, so we write it like that, right? So, and that is given by this what's called the conduction band effective density of states at the band edge, which is dependent on effective masses and temperature and all that, times of Fermi-Dirac integral, and I'm going to just write down the approximate form of it, which is looks like EC minus wherever is a Fermi level over KT. So that's something I think I hope you can also look at it in this way. NC is a material constant, which is kind of you have taken your density of states for a three-dimensional semiconductor that looks something like that, and you have essentially what you have done is you have shrunk it to a large like a very sharp density of states here, and so this is your detailed density of states, whereas this is what you call as NC. This is the effective band edge density of states. So you kind of shrunk it down and look at. So in reality, your electrons will be distributed something like that as the Fermi-Dirac distribution dies. But with that approximation, what you're saying is I'm going to just take a rectangle. As you can see, this is a device design simplification, and I'm going to now say that only a part of that is occupied. How much of it is occupied? That's that exponential factor. That's the picture of band edge density of states. It's nothing. It's something. It's not physical, but it assists in the design and understanding of that. Similarly, the valence bands whole density is equal to when I write approximate, I'll switch between approximate and so that will look like Fermi level minus the valence band edge over KT, and here the temperature is the understanding is the carriers or these electrons and the holes that you might have, which will be, again, valence band density of states will look like that. And here you have NV, and you have maybe some holes occupying there. Okay, so, and the holes, so in other words, the way I should draw it is, again, you might have some holes like that. So, the dashed regions are the occupied. So you have electrons filled, but a little bit missing here, right? I mean, that's the holes. Are you comfortable with this? I mean, if you haven't, I go into some detail in the other lecture videos and in the book as well. So now when you take n times p, which is the, and I'm going to kind of switch back to equal signs now, and you get nc times nv. And you can see from here the exponentials, the Fermi energies will cancel, and you end up with basically conduction band edge minus valence band edge, and that happens to be the band gap over KT with a minus sign in the front. Okay? So where this is obviously one of the characteristic quantities about any semiconductor, elemental, compound semiconductor, doesn't matter. So, and this is this quantity is sometimes called the square root of this thing is called Ni, or the intrinsic carrier concentration. That's how many electrons you have at equilibrium in a semiconductor. So this is called the law of mass action. Np is equal to Ni squared. In at equilibrium, your electron density times the hole density will be equal to Ni squared. And you see right away it has a very strong dependence on the band gap, exponential. Very strong dependence on the band gap. And that's a game we're going to play very well, a lot in compound semiconductor design, because you can change the band gaps in heterostructures in a very clever, in a nice way when you grow the materials. Okay? This is a very important quantity here. Okay? So, now this is all true. The thing is, we have written it down in this way, but the moment I start doping the semiconductor, now all I'm doing is I'm moving the Fermi level, and I've doped it, meaning I take gallium arsenide, I replace some of the gallium with silicon, maybe out of the 10 to the power 22 atoms per centimeter square, I've doped it about 10 to the power 17 of the gallium atoms I've replaced with silicon, so that's an N-type donor. So my Fermi level has gone up, but all this stuff I wrote down still stays the same. I mean, it doesn't change because the thing is still under equilibrium. It's just chemically slightly different. Out of the, a small fraction of the atoms are not gallium, they're silicon, but chemically it's just one material, it's under equilibrium, so all these relations still stay the same. They don't change. What changes are the Fermi levels, right? That obviously changes. Where is it compared to the band edges? That changes, right? And if the donors or the acceptors are such that they are completely ionized at room temperature, as you remember, this part I'm not going in detail, but a donor level will introduce a state here, which is slightly below the conduction band edge. So this would be called the donor activation energy. Typically, you want it to be very shallow, maybe 10 MeV, something like that. So what does that mean? So essentially, you have a silicon atom with an extra electron compared to gallium. Gallium is group 3, silicon is group 4. So an extra electron, and that extra electron, silicon would provide 3 of its electrons to form chemical bonds with 5 atoms of arsenic or nitrogen, whichever, gallium arsenide and nitrate. But one is left out. And that electron can be bound to the silicon atom, or it could be completely unbound. I mean, it can come off. And the way it comes off is at room temperature because of vibrations and crystal vibrations. The electron gets kicks of energy kT, and it gets ionized into this band, and then it can move around. So that's the whole picture. So let's assume they're completely ionized. Similarly, so this energy is the donor binding energy, or the and similarly you'll have acceptor states here with acceptor binding energies EAs, and if they are relatively small, if the donor and acceptor binding energies are kind of smaller or of the order of kT, then we're going to make the assumption at this stage that at room temperature they are all completely ionized. If they're not, you can always find out what is the Fermi level at any given temperature by balancing the charges, and total negative is equal to total positive will give you where's the Fermi level. Always, I mean, that's the trick to play. But if this is case, it simplifies a great deal. The total electron density in the semiconductor is going to be equal to, if you have an n-type doped semiconductor, it's roughly equal to the donor density because all the donors are ionized. So you have put in 10 to the power 17 donors here, so all of the electrons have ended up in the conduction band. So how many electrons do I have in the conduction band? That's roughly equal to the donor density. Okay. So that's something you control completely. And what will be the hole density in the same semiconductor? We're looking at an n-type semiconductor, right? So the hole density, how do you find that? You just use this, right? Mass action law. Now you can see right away it depends very much on the band gap as well, right? Not just your dopant density, but also on the band gap, very importantly, right? So what we did here is the electron density in an n-type semiconductor. I'm going to label it as sub n, okay? And the hole density in an n-type semiconductor. In a n-type semiconductor, which is doped to be electron rich, there are also some holes. Right? So that's the, and so this would be called the majority carrier, right? And this would be called the minority carrier, and if names don't sound reasonable, I mean, you realize that let's say the donor density is about 10 to the power 17 per centimeter cube, and Ni depends on the band gap and all these things. So Ni is like square root of this thing here. These things are all dependent on effective masses of the bands and the band gap. That's all you need to know for this. And for silicon, it's about 10 to the power 10. So Ni for silicon at room temperature is roughly 10 to the power 10 per centimeter cube. And for gallium arsenide, so it goes down exponentially. So silicon band gap is 1.1 electron volt. Gallium arsenide is 1.4. Gallium nitride is 3.4, so this really shrinks very fast. So you can see, I mean, if it's 10 to the power 10, for gallium arsenide, it means maybe like 10 to the power 3 or something like that. You can just do the numbers here. And from here, right away, you get that the hole density will be 10 to the power 10 whole squared over 10 to the power 17. So that's 10 to the power 3 per centimeter cube, right? So you can see the reason why they're called majority or minority. This is 10 to the power 17 per centimeter cube electrons. In the same n-type semiconductor, you have 10 to the power 3 per centimeter cube holes. Right? So, and then the 14 order is different. So it's majority and minority carriers. Okay. So okay, are we comfortable with this? I mean, this is very basic device or semiconductor, physics. So what I'm trying to get to right now is from here to get an estimate. If I tell you what is the doping density, you should be immediately able to tell me how much, where is the Fermi level, and I think from this sort of relation, you can see right away that if you know, because n is roughly equal to the donor density, and that's equal to conduction band edge, EC minus EF over KT, right? So that immediately tells you where is the only unknown in this thing here now is where is the Fermi level. So you can calculate from here right away where is the Fermi level. Band edge density, all these are known, and so what you'll get here is the Fermi level, or let's just do this. So EC minus EF is equal to KT natural log, right, of NC over NV. So there's a minus sign, so I flip the natural log and all that, right? And maybe a better way to just to kind of remember this is that the Fermi level minus EC is KT times natural log of ND over NC. So this is, to me, depends on how you think about it, but this is a little more easier to remember what's going on. Because the way to think about it is the NC, which is the conduction band density of states, effective conduction band edge density of states, is of the order of 10 to the power 18 per centimeter cube. Of the order. Could be 2 times, could be 3 times, or so, depends on the effective mass and all that, but this is of the order. Right? And so this is where we need to have a little bit of a feel for these things. So of the order 10 to the power 18 per centimeter cube, and what it's saying is you can see that if the doping density is less than 10 to the power 18 per centimeter cube, we have natural log of something less than 1, which is negative, right? Right. What does that mean? It means the Fermi level is below the conduction band edge, right? So that's the, just to have a feel. So Fermi level is somewhere here, or in band edge picture. If we draw the band diagram, Fermi level is kind of somewhere here when the doping density is lower than NC, and when it exceeds 10 to the power 18, obviously this becomes larger than 1, and Fermi level kind of enters the conduction band, or just about merges, and then it starts entering, if it goes very high doping, right? So if you have very high doping, it can go in here or something like that, and what you'll see here is the natural log function changes very fast when you start from here and come up here. But once you hit here, it slows down quite a bit because the density of state is very high, and the carrier density is increasing linearly with doping. But the Fermi energy was increasing logarithmically with doping. So it once enters the DOS and all that. Okay. So from here again, the estimate is if right away you can see that if the doping density is exactly equal to NC, then your Fermi level is kind of right at the band edge. Right at the band edge is just about what you call degenerately doped, and let's assume let's assume it's 10 times. Let's say the doping density is 10 times. This is just to give you an estimate. If doping density is 10 times, then your Fermi level minus EC is 26 millivolts. KT at room temperature is 26 milli electron volt. Right, times natural log of 10, which is, because that's 10, right, this over that. So that's about 2.3 or so, right? So you get, you get in about maybe 60 milli electron volts into the band edge, so order of magnitude, right? Similarly, if doping density was 10 to the power 16, so 10 to the power 16 over, which is very low, 10 to the power 16 over 10 to the power 18 will be like negative of natural log of 100, right? This makes sense? So you'll be like maybe 600 MeV below or something like that. No. So like 3 times that or 2 times that, right? So you can estimate how much. So that's something very useful. If you want to design device and you want to place your Fermi level somewhere, you can always use this as a first shot, and then you can make it more and more accurate. Yeah. Any questions? Yeah. All right. If not, let's move to the next step, which is I think anyway, I'm going to just erase this now. But leave this on here. NP is equal to Ni squared. So what we are interested in now, and we'll see that right now we have clearly, if the band gap is well defined, then you have no problem. Everything looks very nice. But the moment I go to a semiconductor where I have a band gap that may be looking something like that with space, and I think this is the beauty of the compound semiconductors, that you can do that. You can change the band gap continuously, right? You can change from large to small, mix and match them. Now it's not very well defined, because what's the band gap now, right? It's changing, and that's something that's where we are going right now. But before that, let's actually just also review the most, to me at least, the most important semiconductor concept and device concept, which is the PN diode, PN junction. So we'll just review it, and both the traditional semiconductor and the PN diode will then make them heterojunctions, compound semiconductors, and see what changed. So that's what we want to achieve today. Yeah. So a PN junction is, you take a p-type semiconductor and an n-type semiconductor, and we're going to start with a homojunction, meaning the band gaps are the same. It's the same semiconductor on both sides. But because the left side is p-type, let's say, and the right side is n-type, and this is my conduction band edge, valence band edge, right? What I want to kind of start thinking about now is what happens when you put them together in a junction, right? So we already know what happens if it's standing by itself, right? This is what happens, NP is Ni squared. You have majority carriers, you have minority carriers, nothing else is happening, right? And now we are going to put the two together, P and N. So p-type semiconductor, because you have doped it with a certain acceptor density, and you have doped this with certain donor density, your Fermi level is kind of somewhere here. And the n-type semiconductor, let's say the Fermi level is somewhere there, right? I'm not going to label them now because it's not a uniquely defined energy. They're different, right? And I think, yeah, so so this is this is the vacuum level, not EV, valence band edge, okay? And this energy would be called the electron affinity of that semiconductor, vacuum level to the band edge. And these things are something you can measure by all kinds of spectroscopic measurements, and you can basically kick it with photons, change the photon energy, get electrons out of here. If you have some electrons hanging around here, you can kick that out and look at all these electron affinities and all that stuff. Yeah. So and this quantity here, from Fermi level to that, is called the work function. That's the traditional definition of the work function of anything. Fermi level to vacuum, right? So that's how much energy. But I think the semiconductor is somewhat strange that your Fermi level is inside the band gap where there are really no electrons there. I mean, that's okay. And the work function of any semiconductor is completely tunable. As you can see, you can go from valence band to conduction band. It's heavily tunable. This is something that doesn't happen in a metal. Right? You cannot change the work function of a traditional metal, at least. Okay? So now what happens when you put them together? And then this is where you can see now that the Fermi energy. We are going to now kind of invoke a very important principle, which is what causes whenever two objects are in equilibrium or in independent contact, such that they can exchange particles, or they can exchange both particles and energy, if you might. In that case, they will end up sharing the same chemical potential. Chemical potential is a measure of the total energy of the system, and when you put them together, they'll share the same chemical potential. And I'm following the notation in Rocket's book here. The chemical potential we're going to label as mu, And don't get confused, because we're going to use mu sub n as the mobility later. So right now mu is just the chemical potential. I think this is something you have seen probably multiple times. Whenever you have a chemical potential, whenever you have two different dissimilar materials and you put them together and allow free exchange of particles and energy, they will end up with the same chemical potential. I mean, the flow of particles energy will be such that it will lead to, after a certain amount of time, the same chemical potential throughout the system. Right? So that's the idea. And that means the flow of anything, particles energy, is always driven by something of this form. Right? If there's a difference in space, this is what's the driving force for flow of particles. We are looking at electrons here primarily. So if you have, on the other hand, two solutions, one has a certain concentration of metal or of ions, the other has a different concentration, put them together, then it will be ions, not electrons, and so on, right? So you have so chemical potential will equilibrate. So, and the force that will drive that is typically equal to some constant times the rate of change of chemical potential. The force that drives that. Force as in newtons. This is the force. Chemical potential, again, I mean, the nomenclature is very sometimes confusing, sometimes called the electrochemical potential, because the electrical energy is distinguished from chemical energy and so on. But I think, hopefully, okay. So this is the chemical potential, and for us, this chemical potential is equivalent to the Fermi energy, or Fermi level here. Now, again, Fermi energy and levels can be sometimes in textbooks referred to as different things, but that's what we're going to refer to it at this point. Okay? And right away you can see that the Fermi energy of this thing is here, Fermi level is here, so there's a difference, there's a gradient, right? And therefore there will be flow of particles, right away. So there's a force that is going to move particles. Which way? We're looking at electrons, so it will move, Fermi level here is higher, so there'll be some sort of a gradient, and that will essentially push electrons this way. And we'll see very briefly in a short time that the holes will also go that way. And so, or in other words, we just look at electrons. So essentially there's a gradient in electron density. Electron density is very low here, very high there, and therefore there's a flow. Okay, so now the chemical potential can if we look at the current of particles, the current density, ampere per centimeter square, current density, that is carried by some particles. At this point we're interested in electrons, so Q times, let's say I'm looking at the n side, electron density times the mobility of electrons. This is, don't get confused with that mu. This is the mobility of electrons times the d mu by dx. What did I do here? Essentially, we're kind of calculating once you know the force on the electrons, you have the velocity, and these constants are essentially electron charge times the mobility here, if you want to think of it that way. This is the current density. Current is driven by a difference in chemical potentials. If you have no carriers if you have no particles, there is no current, right? Current can flow, but if there are no particles, there's no current. So and this is the picture, which is actually a little more accurate, which does not, at least in the first place, does not invoke electric field. But this is the electric field will be a consequence of this. It's not a reason for that. And so rate of change or the gradient of chemical potential. Let's look at what the gradient of chemical potential can be. The chemical potential can change if you change the electrostatic potential, meaning I can take just an n-type semiconductor with no p-n junction, and I can apply a voltage across it, kind of move this to something like that. When I apply voltage, the energy eigenstates kind of move like that. And there's a gradient in the chemical potential itself, or the Fermi level, which effectively I'm saying now they're the same. There's a gradient. So that's called an electrostatic force, due to an external voltage. It's an electrostatic force. So in other words, if I have a potential change in space, and I think so that's what we call as an electric field. let's just not confuse things here. So electric field I'll label as f of x. Okay, electric field. I think in rocket there is a curly E and then there's a normal E and then E sometimes is used for energy. I'm just going to use F here for field. Okay. Electric field is negative rate of change of potential, that we know, right? Negative gradient of potential, so that the electric field. Okay, let me just write this down. You can say that if there was only electrostatic forces present, then this would be dmu by dx, rate of change of potential. Yeah. Okay, is that if there was only electrostatic forces present? So the rate of change of chemical potential. The one way to look at it is if we're looking at electrons. This is electron charge times the potential energy. So that's how they're related and all that. Okay. So that's the electrostatic potential. On the other hand, the very important thing in a PN diode and many semiconductor devices is not just the electrostatic potential, but so this is if only if Vx is present, right, and no gradients in carrier density. That's what we mean. If there are no gradients in carrier density, that's your total field. Now, if you do have gradients in carrier concentration, which is what you have here, if I were to plot this here, the carrier density on the n side is n times n, which is very high. The electron density on the p side is n on the p side. So we saw it could be like 10 to the power 3 per centimeter cube. This could be 10 to the power 17 per centimeter cube, right? We just saw that on the p and the n side. And as a result, you have a huge gradient in the carrier concentration, right? Very big gradient. Right. And I think that again we can kind of go back and derive it in great detail, but let me just write it this way. You can hopefully agree with me that the d mu by dx due to a chemical the particle number gradient here. So see, this is clear that the electrons will be driven this way. They'll try to flow that way to equilibrate the particle energies and so on. And we also know that electron density is Nc, e to the power Ec minus Ef over kT, right? And we just we can rearrange this and write it as Ef minus Ec is equal to kT natural log of n over nc. Right? That's fine, right? And I'm saying this has a physical meaning. Let's say I do not have any electric fields. I mean, actually, electric field will end up developing anyway. This has a physical meaning of mu for you. So, mu. And when you take the derivative of d mu by dx, which is what we're looking for, the derivative of chemical potential, then you're taking a derivative of natural log of the carrier density. Natural log of the carrier density. Carrier density is clearly changing with x, right? So, and this quantity will be, let's see, so chemical potential, so you get kT, and let me maybe write this whole thing down. So d over dx of natural log, and what I'm saying here is, I think you can see, I'm just writing natural log of n, and I think, yeah, does that make sense? I mean, that's how it's going to be. There's a conduction band change as well, but initially there is none, as you can see. I mean, the conduction bands are flat, and now we're saying how much flow is happening, and this is it, right? Just, whenever you're in confusion, you can check the dimensions. I think I already can see that, so potential is voltage, is energy over distance, kT is energy, there's distance, logs have no dimension and so on. You can just check that. And d by dx of natural log of that is basically just dn over n, right? I mean, that much. Right, okay. So this is the change in chemical potential due to concentration gradients. This is the change in chemical potential due to electric field. And in general, both of them are present, right? Both of them are present. So the total change of d mu by dx is this plus that. This is typically called diffusion. This is called drift. Okay? But they have the same origin. So now I can plug both of those things in. So there will be this plus that. And you write your current now. I'm going to erase this part. So J, due to electrons only, we're just writing it for electrons, is equal to Q and what did I write there? Q times electron density times the mobility. And what I just kind of trying to justify is I have a quantity here which is basically just the electric field plus this is the drift term, the first term. dV by dx is because of that, plus dV by dx because of that, which is diffusion. So I get kT over electron density natural log of carrier density over, what did I do? dN by dx, sorry, dN by dx. Okay, so that is that fine? And from here, you know, this is how it's typically written. You break it up, and then you see here what you end up getting is n. So n's cancel out, n and n cancel out here, and you get a mobility times the temperature times dN by dx. Okay. And in fact, so this quantity, the total net current of electrons and holes, you know, if you had equilibrium situation where you had you know, an internal electric field due to some concentration gradient because of you had doped something heavier and something lighter only with electrons, then the net current when you don't apply an external voltage must be 0. Just from that argument you can justify that you know, this quantity, these two quantities are not completely independent. In fact, there's a, you know, very important relation between them for non-degenerate semiconductors that or rather you can define this constant, which is the diffusion coefficient, as diffusion coefficient over mobility is kT by q. This is the Einstein relation. You probably have seen this multiple times. So all I'm saying is you know, I just take the mobility here and you know, take you know, the q will cancel, and rather, okay, so I'll just end up getting q and dN dx, you know. So that's what's going to be drift plus diffusion, right? And this gives you the current in not just n-type semiconductor, p-type semiconductor, p-n junction, heterojunctions, everything. You know, this is going to give you a current. And I think we know that pretty much all of interesting applications of these materials will require you to apply a voltage and measure some current, which will do something, or you know, shine light on something and that generates an open circuit voltage, or measure currents in response. So this is essentially what connects input and output now for all devices, you know, this sort of relation. So this is the fundamental transport equation, and oh, that's not working. I just want to make sure that I'm going covering the details here. Okay. So is that clear? I mean, that's the net current, and from here we will now see that the current density in a PN diode will essentially look like a certain constant e to the power qv over kt minus 1. But before that, let's just look at the diode characteristics a little bit, at even when you do not apply a voltage, 0 voltage. And from that we can actually conclude quite a few important things and start justifying the reason for looking at compound semiconductors to start with. So, okay, so let's look at the PN diode. I just started sketching this picture, and again, it's probably quite a bit of a repeat for some few, but it's all right. So EV, EC, and we said P on the left side and N on the right side, right? And P. So when we put these together, we have, you know, very much higher density of electrons here than here. So the electrons will flow from left to right. And what we're going to now sketch is what are the charges that develop in response to that. Because remember, any doped semiconductor by itself is completely charge neutral. It has exactly equal number of negative and positive charges, right? No matter whether you dope it n-type or p-type. If you have 10 to the power 17 electrons in the conduction band, then which are negatively charged, that doesn't mean that the semiconductor has 10 to the power 17% extra negative charges. They're equal and opposite positive charges, which are the donors, which are ionized, which gave you those electrons, right? So there's a background fixed charge, and then these mobile charges are negative. The fixed charge is positive, they're exactly balanced, right? So any semiconductor at equilibrium is completely charge neutral. But now you're going to put them together and you're going to let electrons flow out of this. Right away you see this will get positively charged, right? And this will get negatively charged. Right? I mean, it's going to lose electrons, so it's going to get net positive charge. And the reason for that positive charge is obviously now you had donors, and which was basically equal to this, right? And this is acceptors, and donors are positively charged, and acceptors are negatively charged. So what we'll end up getting is a slice of charges, negative charges from here will be lost, and you are going to have positively charged donor atoms that will be essentially kind of unscreened or exposed now. And similarly on the left side you'll have negatively charged acceptor ions that will be exposed now. Okay. Does that make sense? I mean, okay. So you get a depletion region. It depletes electrons, it depletes holes, and you get two depletion regions, Xn and Xp. And one of the reasons I'm doing this in detail now is right away we're going to develop something which you may or may not have seen, which is you can estimate what would be the breakdown voltage of a PN diode from these considerations, and how does it tie into the band gap, and the reason for compound semiconductors will kind of become very clear right away as you get. So this is basically your electron, or this is the charge density, fixed charge. This is the total net charge density. Everything is neutral deep inside the P region. Everything is neutral deep inside the N region. But the moment you go near the junction, there is a certain width, which is the depletion width, inside which there is this charge dipole, which is fixed. It's not, these are not mobile charges anymore. Okay? And all these quantities are, you can calculate analytically. Again, just to be clear, these are approximations. There are, carrier densities don't change abruptly like that. So there's always these tails, but this is a great approximation. It works very well. Probably the most important relation in semiconductor devices is this. It's not the quantum mechanics as much as it's the Poisson equation, which is the electrostatics. I mean, depends on what sort of device you're making, but this is Poisson equation, relates voltage to charge. Right? Voltage to charge. This basically, the Gauss law number 1, right? So charge and voltage relationship, right? Negative curvature of the potential is equal to the charge, or in other words, charge determines the curvature of the potential. Charge determines the way the potential bends or curves. Right? If there's no charge, potential can be either constant or linear, right? If you take a linear potential difference, then double derivative will kill it, right? If it's constant, it's going to be so if there's no charge, no net charge, the potential will stay flat or it will change in a linear fashion. The moment there's charge, it's going to curve. Right? Does that make sense? I mean, that's the physical meaning of Poisson equation. And now we're going to just apply that here. Also, we know that the electric field is negative gradient of potential, right? So you see, really, Poisson equation is equivalent to saying that the electric field gradient is equal to the charge, right? By dielectric constant, and that's the dielectric constant. And remember, dielectric constant also plays a big role. Narrower band gaps have larger dielectric constants, so it will change the curvature accordingly, right? If you have a narrower band gap material, the denominator is very large, so it doesn't curve that much. Does that make sense? Right? If you have a much smaller dielectric constant curves a lot more, right? So it bends a lot more, and things like that, right? So we can. Okay, so and so from here right away you see basically all I'm trying to say here is electric field is an integral of your charge profile, and potential is an integral of your electric field profile, right? From here, right? So, but we already found our charge profile, and I know how to integrate it. It's not a problem. I just integrate this, get my field, right? And integrate field, get how the band will look in the end after all is said and done, right? And the one thing we can say is after all is said and done, after the charges have moved and reached equilibrium because of the concentration gradients and chemical potential difference, in the end I will have some electrons lost here, so essentially this is how it's going to look in the end. And the whole thing now is still charge neutral, because you started with charge neutral, this was charge neutral, that was charge neutral. You put them together, the thing has still got to be charge neutral, right? So the total positive charge here must be exactly equal to the total negative charge here. This is really a dipole, right? And therefore, from here you can say right away, because the area here is dopant density times the thickness, ND times Xn must be equal to acceptor density times XP, right? So that's clear, right? And you also know that Xn plus Xp is equal to the total depletion width, right? So from here you can also write down that Xn is equal to acceptor density by sum times width. Xp is donor density over sum plus times width, right? I mean these things should be standard, right? It also tells you something interesting, that if you dope one side very heavily compared to the other, let's say my N side is much more heavily doped, N++, that's how it's typically labeled. P side not very heavily doped, lightly. Okay? So ND is much larger than NA, let's say, right? So in that case, you can check from here if ND is much larger than NA, so the depletion on the N side, on the heavily doped side, will be actually very small, and this will be much larger. So most of depletion is on the lightly doped side. So that's another very important physical behavior of p-n junctions. So the depletion region, and I think you can see in pictures also that if you dope it very heavily, for the same area you get much thinner depletion here, much larger depletion on the other, because the areas have to be preserved. So that's the electric field. That's the charge profile, and then we come to electric field profile, and we just saw the electric field is just an integral of this. An integral, you can pictorially do this, at least for this sort of structure. It's a p-n junction. It's a 3D semiconductor in this direction, and the plane, you have a metallurgical junction. Electric field is an integral. Integral of negative constant is a straight line, right? And then it reaches some value, and then it kind of accumulates back, and then you go to 0, right? So that's the electric field profile, right? So simple enough, right? Just like that. What is the magnitude of all this stuff? So field is just an integral of this, and this is NA. So I think you can see right here that the maximum field I reach here is equal to an integral of dx times NA times electron charge over epsilon s, going from, let's call this 0 to xp, right? I mean this length is xp. So right? So that thing is just, it's the most trivial integral, right? So you just get that. That's the maximum field in the junction, and just from this sort of picture, you see right away that it must be also equal to exactly Q times donor density times the depletion on epsilon, meaning you start from this side or you start from that side, you get the same value, right? Now we'll see that. I don't know whether we'll reach that today. Okay, in a heterojunction, this is not true. The field max on this side can be different from the field max on that side. In a heterojunction, when you have two different dissimilar materials, it can be different. I know we're going to see that, and its consequences as well. Yeah. Okay, so that's the maximum field, and what was I going to write here? From here also, what we can do is relate the maximum field. You see, right now these two quantities are unknown for us. We don't know them yet, meaning, and we have to relate it to something physical now. And the only things we know are what are the doping densities, what are the band gaps, and right now we're looking at a homojunction, so the band gaps are the same on both sides, and the band edge density of states. We know the materials and the doping densities and nothing else right now. So all these quantities, xn, xp, width, f max, the field, maximum field, everything must be related to those quantities, and we just want to write them out analytically now. Is that clear? Any questions? No? Okay. So let me just erase that part again. Because the potential is an integral of the electric field, you can see now a constant function, you integrate, a linearly changing function, when you integrate it, it's going to be a parabola, right? It's going to be a parabolic curve, right? And what does that mean? It means that basically the bands are going to bend in a certain way. It's going to bend in a certain way, and such that the Fermi levels become equal and the bands bend in a certain way, and you will get a band diagram, right? And the band diagram, the most general way of drawing the band diagram, and the vacuum level must bend as well. Because, by the way, these are things that are also in that video if you want to look at it in more detail. But okay, so the Fermi level becomes, or the chemical potential becomes the same everywhere. But now you see that your p side is here and n side is here, and the conduction band edge must start bending. So it must start bending in a parabolic fashion, right? And then join back here. So the curvature on this side is determined by the negative charge, on this side is determined by the positive charge. So here you see it curves this way, here it curves that way, right? So these are also very characteristic quantities of any p-n junction. And in the homojunction, the band gap is always the same. So it's maybe not sketched in the right way, but something like that. Okay, so how much potential? So the other very important question: what is the area under this? Is basically the total amount of band bending here, right? Total amount of potential difference, and that quantity is called the built-in voltage of any diode, right? Built-in voltage of a diode, of a p-n diode, and sometimes called a contact potential, and all kinds of other things, like that. So, and the built-in voltage, you don't have to go through all this business to do it. Built-in voltage, you saw that before we put it together, I already knew that the Fermi level on the n side. Okay, so the Fermi level on the n side before you put it together was equal to EF minus EC was equal to KT natural log of the doping density over NC, right? We wrote that. And the Fermi level, let's write it on n side here, and this is a bad notation for, actually, I don't want to, okay. Minus EV is KT natural log of NV over NA. I think you can go back and forth here. So the built-in voltage is basically what it was before you put it together minus this, this minus this, the difference of the two chemical potentials. And I'm not basically doing that now, but essentially what you'll see is, there'll be a band gap and all that stuff here, and what you'll end up getting is when you just do that little difference, Q times VBI will be KT natural log of the doping densities on both sides over Ni squared. So you get a EC minus EV will give you a band gap, and then it'll get absorbed and go into this intrinsic carrier density. So that's the built-in voltage, which really clearly depends on what semiconductor you choose, which is buried in the band gap, and the doping densities on the two sides, Na and Nd. It should be clear that if I have, maybe a better way to write it, a more general way to write it is not write Na and Nd, but write it as N on the N side times P on the P side. Does that make sense? Or oh no, just a second here. Yeah, okay, that's actually correct. Yeah. N on the N side and P on the P side, because if your donors and acceptors are not completely ionized, then this is the more accurate relation. It's the majority carriers on both sides. And another way to also look at it is remember your electric field was kind of negative rate of change of potential, and you can substitute by chemical potential, and you are if you have concentration gradients, you can integrate it, and I don't want to get into that, but integrate the field and you get the voltage, and the carrier densities on both sides will essentially determine what is your built-in voltage. So, okay, and that happens to be exactly equal to the voltage here is exactly equal to the area under the curve, because the integral of electric field is the voltage, right? So that's exactly equal. Right? So now we can find everything else now from here, right? Because that the area of the triangle is basically maximum field times width. Half of that, it's half base times height, right? So that's your maximum field. So you can just write it as F max times width of depletion is equal to VBI, right? Okay, sorry, half of that. And from here, let's actually write that down. So F max will be half. Let's write it as Q times ND times Xn over dielectric constant times the width is Xn plus XP, right? And equal to VBI. But I think now that Xn and XP are related. They're not independent. In fact, Xn over Xp is equal to Na over Nd, right? The doping densities is because of the charge neutrality condition, and so you can add 1 on both sides and get numerator becomes Xn plus Xp. So that's just the depletion width over Ft is Na plus Nd over Nd, right? So I think I should have maybe done it a different way, but that's fine. So let me just write XP over there. I think I'm going round and round, and that's fine. So the whole the p-type depletion width is equal to the total depletion width with this ratio in front, and so I'm going to replace this with Na XP. Why? Because I know that now. Okay? In terms of depletion width, I'm trying to find the depletion width. Okay? So I just plop that in here. And what you end up getting is NA/ND over NA plus ND, right? Times, what does this become? There's a W here and there is a W here, so you get a square of the width, depletion width. And you now know your depletion width, because this is the only unknown in this whole equation, right? So the depletion width is and then this is a kind of important result. Width is 2 epsilon dielectric constant over Q, 2 epsilon times VBI, VBI times, and see this is actually the way it shows up is NA plus ND, right? When you take this, this over there. So you get 1 over Na plus 1. They kind of add in parallel here, square root. Right. That's everything on the right side is known. So also what you notice right away is that the depletion width is obviously dependent on the dielectric constant. Higher is the dielectric constant, larger is the depletion width. It also kind of makes sense because it was curving very slowly with a small. Sorry, what did I say? So higher is the epsilon, larger is the depletion width. That's correct, yeah. Other things, doping. If your doping is very, very heavy, depletion width shrinks, right? And so on. So those are the physical quantities here that one needs to look at. Right? VBI is that, right? So you can substitute all that. And there will be like a doping density inside there too, but that's logarithmic. Right? That dependence is logarithmic, right? Does that make sense? Natural log of, again, going back to our first result here, this is NA and NB. So that depends logarithmic, but this is, this is from electrostatics. So this is a stronger dependency. Is that clear? So that's just the depletion width. You can plug in numbers for doping density of 10 to the 17 per centimeter cube on both sides. Maybe we'll get a couple of 100 nanometers for most semiconductors. Maybe half a micron if your doping is even lower. If your doping is extremely heavy, it's maybe like 30 nanometers or something like that, the depletion width. The field, as you can imagine, will also, from here you can right away write that the field F max, right, is equal to 2 times VBI divided by this whole quantity here, right? Divided by this whole quantity from here. And so, actually I want to write it because I'm going to use it in a little bit later. 2 VBI over the whole thing. Q, I have to mentally do that. NA, ND, and there's a VBI in the numerator. Okay, so yeah, something like this. Okay, maybe there's a 2 here. I forget, something like that. Okay. But the physical dependencies are like that. So that's the maximum field. And the maximum field is a very important parameter because when a semiconductor, when you apply voltages now to the diode, then that will determine, at what point does the diode break down and things like that. It's a very important parameter, the maximum field. If your doping densities are relatively low, the maximum, let me give you an estimate. A very high field is 1 megavolt per centimeter. That's a very high field. Fields are typically in semiconductor devices looked at, in units of volts per centimeter. It's a mixed unit. And a very high field is 10 to the power 6. It's a megavolt per centimeter. So typically, if you look at narrow band gap semiconductors like silicon, they cannot handle this kind of field. They'll break down way before that. Wider band gap semiconductors, most of them are compounds. Gallium nitride, gallium oxide, aluminum nitride. They can sustain much higher, 4 megavolts, 5 megavolt per centimeter. Silicon breaks down at a few, I think, kind of 100-ish kilovolt per centimeter. So it's 10 order of magnitude smaller. So. And you can plug in the numbers, etc., and check this here. Okay, so okay. Now what I want to say is I'm going to apply voltage to it and ask what happens to this diode now once you apply voltage. First thing first, obviously there'll be some current flow, right? Because at 0 voltage the drift and diffusion kind of exactly balance each other out, and there's no net current. But when I apply voltage, there's a current like this now. And I'm not deriving it right now, but what I want to do in the class today on is look at what's an estimate of the breakdown voltage that you can apply across a PN diode. Estimate of that, and that will come out from here. So remember the question I'm asking is what's the voltage that you can apply across a PN diode before you break it down. So, okay, we'll come back to this part a little later when we look at the current aspect of current flow. Let's erase that. Yeah, even that part it can go now. So when you so we're going to apply a reverse bias, meaning on the P side, if you want to think of it. So let's say this side is grounded. And a reverse bias means that I'm going to apply negative voltage to the P-type side or positive side. That's reverse bias. And negative voltage, whenever you apply a negative voltage to anything, it means I'm trying to put more electrons or charge it up negatively, Trying to put more electrons on that electrode. You can think of this whole P region as an electrode. And the way that the system responds is basically the P region wants to be more negative now. Right? But the P region, how can it be more negative? It can be more negative by stretching out the depletion region. It can have more negative charge. You see that, right? And actually equivalently, because the whole system is going to be still charge neutral, you're going to, this side is also going to stretch out. Because everything is always charge neutral, no matter whether you apply voltage or not. Because all that the battery is really doing is when you're applying negative voltage, it just is moving charges around, it doesn't provide extra charge, right? So it's basically pulling out the electrons from this side and just, essentially that electron charge shows up as a negative fixed charge here. Does that make sense? I mean, that's what's happening when you're applying a reverse bias. It stretches. Okay? And because the depletion, the doping densities we are assumed to be uniform, all that's happening is, the charges stretch out, you integrate the charge, your field becomes like that. The slope of the field doesn't change. The slope at which the field is increasing doesn't change at all, right? Because it's just dependent on what is this doping, and that's fixed, right? So the slopes don't change, and the field kind of starts doing that, and your, maximum field starts increasing. So the whole thing kind of just rigidly moves like that, right? That's the consequence of Poisson equation. It just rigidly moves. And all the extra voltage you have applied is going into this area. You can see, every voltage you apply is just the extra area here. You can just basically do your geometry and find out what's the stretched region now, right? It's very straightforward, really. In fact, you don't have to do anything. If I ask you the question, what is the new depletion width, you can basically just change this and add, here's my reverse bias voltage, and that's it. There's nothing else to do, right? Does that make sense? So that's it. Similarly, the maximum field here will be VBI minus V applied, or just say applied voltage here, because every argument we had before doesn't change, and in reverse bias V applied is negative, so basically it adds here. Okay? VBI, it adds to the VBI. Does that make sense? Right. So the band diagram, what you're doing is. I think this is where the slides would have been nice, because there were some figures that would help, but that's fine, we can sketch it. So the band diagram starts looking something like that. Okay? So your depletion region has stretched out, and now this difference in the P and the N side voltage is way larger than V up. So kind of minus V applied, but V applied is, if you just say plus the reverse bias. Okay? So you bent it that way. Right? And so now what's going on is we want to estimate, you see the peak field is occurring at the junction. It's not everywhere, it's just at the junction. And there is a certain field at which this semiconductor will essentially, the diode will break down. And there are three kinds of breakdown, and what we are going to talk about now is a process called an avalanche breakdown. We're going to give a very simple picture, and this is from rockets, which I think is intuitive and not overly complicated. So what's going to happen now is the current that flows here is there are a tiny bit of electrons, which is P sub n, n on the P side, n sub P. This is P side, this is n side, and there are very tiny amount of holes here, which is P on the n side. Does that make sense? I mean, these are the carriers that are available. I mean, and obviously you have a lot of holes here and a lot of electrons here, but unfortunately those electrons cannot go up. The barrier is way too high. Neither can these holes come down. This is a barrier for holes. The holes want to bubble up, right? So the only thing left is these electrons, the tiny amount can slide down, and these holes can slide up here. That's the only thing you can do. So the minority carrier will dominate everything here. It dominates the business here, even in forward bias. We're talking about reverse bias now. So they slide down, and now you see that the electrons are going to have a lot of energy, if you apply, say, 100 volts, this is very large. Potential drop is very large. This is about 1 EV or 2 EV or 3 EV, whatever is the band gap, but this could be like really large. And we're asking at what point does it break down. So here's a quick estimate. I think are we already over time? Yeah, maybe just a couple of more minutes and we just finish this argument and leave it there. Okay. What we are going to find now is that the breakdown voltage due to avalanche is going to go as the square of the band gap. We're going to see that, which motivates it's proportional. We're going to see that now. Due to this avalanche process. What is the avalanche process? The picture is very simple. Your electrons are going to slide down, but they're not going to slide down like that. The picture is they're going to essentially go without losing the energy first, and then the electron is going to kind of see the chemical bonds of the atoms here. Okay? And then there are obviously electrons tied up to the chemical bonds. Right? that has formed the solid in the first place, right? And then those electrons are in the valence band state, as you can imagine, right? I mean, these electrons, remember when you did your tight binding model, you basically looked at the band structure of this, and the valence band is filled with those electrons, right? That's where those states came from. And this is conduction band, so it's kind of there, and they're climbing up the conduction band. At some point, basically, this electron is going to have so much very high energy, and it's going to collide with an electron in the bond. It's going to kick it out, and when you kick out an electron from the valence band, what you're left with is a hole, right? It's going to kick it out, but where will that go? That electron. So essentially, this electron with a very high kinetic energy is going to, impart all its energy to create a hole here, and that electron is going to be promoted to this place. So now you have 2 electrons and 1 hole. Does that make sense? Actually, sorry, this electron is going to lose its energy, and there'll be 2 electrons at this energy. So gain some excess energy, and this, you can see right away that the excess energy it must gain should be of the order of the band gap, right? In order to be able to promote an electron from here to there. Does it make sense? And this is the start of the avalanche process. Now these 2 electrons will go, and both of them will reach a very high energy, and then they can kick up 2. So you get 4 electrons and 4 holes. You see that, right? And this is basically the classic snowball effect, right? As it goes down, it grows bigger and bigger. This is avalanche. So this is the avalanching process. And this you can estimate. Is that clear what we're saying? So electron kicks out, creates electron from the high energy electron in the conduction band, kicks out an electron from the bond, creates an electron hole pair, and then there are 2 electrons and 1 hole, and then they start drifting again, and similarly the holes can ionize. I mean, there are all kinds of, so essentially it just keeps increasing. The carrier density starts increasing. So the way to estimate this is, at what voltage will this sort of kind of become very high? You can say that typically the velocity of electrons is this is a very high electric field region, and the velocity of the electrons would be of the order again I'm going to just write it, this is of the order of 10 to the power 7 centimeters per second, of the order of 10 to the power 7 centimeters per second. The electron mobilities, let's look at silicon. It's about 1000 centimeters square per volt second at room temperature, and the mobility is q times electron scattering time over the effective mass, okay? And mass is 0.2 roughly m naught. Depends on what semiconductor you're looking at. The length the electron moves over one scattering event is called the mean free path, right? And that's velocity times the scattering time, right? Mean free path between any 2 scattering events. So that's roughly velocity times, you can rearrange this, mobility m star over tau. Velocity times, so this is the tau, mu m star by q. Yeah, by q. Okay. That's the mean free path. You can plug in the numbers, 10 to the power 7 centimeters per second, 1000 mobility, 0.2 effective mass. You're going to get about 10 nanometers, order of magnitude for silicon. Or depends on the material, but that's the order of magnitude. I think from here, you see, it's moving 10 nanometers roughly before it scatters, and in that time, it must have gained an energy. It must have, in order to kind of cause the avalanche, within that length, it must have gained an energy equal to the band gap, right? Then it can kick out an electron, right? So because otherwise it's going to scatter and not do anything, right? So what's the energy it gains over a length L? That's basically the field times the distance, right? That's the potential, right? So let's say we know the field, and the field, I think you realize right away, we are talking about this avalanche process to happen most effectively near the maximum field, where the field is the maximum, so it's going to be this field. So field, you see this argument, I think this is actually a very correct argument, times field is roughly equal to the band gap, and that's going to give you your breakdown voltage. Make sense? Roughly. Substitute it here, this whole quantity. And so you have all this square root and stuff here. Then VBI minus V breakdown now, right? VBI is minuscule compared to the breakdown. VBI is 0.7 volt or 1 volt or whatever. Breakdown is 100 volt. Right? So you just forget all that stuff. So from here, I think you can rearrange this. I'm not going to write it. And L and all that. You'll see it's basically going to use breakdown square. And there's a nice formula. I don't have the slides up. You can get it from there directly. And this is the reason why, if you take a PN diode, we are typically not talking about breakdown fields as much as what is the breakdown voltage. And if I sketch in terms of the doping density, again, this is doping density plays a very big role, as you can kind of see here. The doping density will play a big role. And now we have plotted the breakdown voltage for various semiconductors. What you'll see is the narrow band gap semiconductor. So this is kind of a log of scale, log of this, log of doping density. And you kind of see like that. And obviously, what you'll see is silicon lies here. Some narrow band gap compounds lie very small voltages, and the highest ones are, the larger the band gap, obviously the larger you have the breakdown capability. So as an example, for if you were to look at, so this would be, for example, silicon. Gallium arsenide is slightly larger. So for the same doping density, you can have way higher, orders of magnitude higher breakdown with a wider band gap semiconductor than a narrow gap semiconductor, and many of these are compounds, compound semiconductors. Okay, so let's stop here. Hopefully next time we'll have a little better. Oh, we're 5 minutes ahead, but again, Thursday no class. I think you probably have seen the calendar. Thursday I'm traveling, but Friday we have another makeup. It's Friday. And it'll be in this room, I think, the makeup. I'll send out an email.